On a quiet night in late March 2025, a peculiar flicker appeared in the automated sky surveys. Not a flash, not a flare, but something stranger. The telescopes of Atlas in Hawaii caught it first. A slow pulse of light, rhythmic yet unpredictable, glimmering in the cold expanse between Jupiter and Saturn. It wasn't bright enough to draw attention, yet it refused to fade. Night after night, it shifted in ways no one could quite explain. Its brightness rose without a clear cause, dipped again as though veiled by something unseen, then rose once more. Within days, data analysts began to notice a pattern buried in the noise, a strange, inconsistent heartbeat of light. By mid-May, the TESS space telescope joined the vigil, and that faint pulse transformed into a riddle. Across 6.4 astronomical units of emptiness, something was stirring, glowing faintly red, as if lit from within. It shouldn't have been active, not out there, where sunlight is weak and cold dust reigns. Yet, in the silence of space, it began to brighten, and as June unfolded, its light curve grew restless, almost alive. Some astronomers whispered that this could be the signature of a volatile surface erupting ahead of schedule. Others suggested geometry, reflection, or data error. But no one could deny it anymore. Something unusual was happening, and it was happening far earlier and far farther than any model had predicted. Tonight, we embark on a new journey, where the theme of 3I, Atlas, scientists are divided over its unusual light curve, appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. When the first traces of 3I Atlas were captured by TESS in mid-2025, its glow was faint yet alive, suggesting that the visitor from interstellar space was already active, long before crossing Jupiter's orbit. Soon, its color began to drift from deep red to near-solar hues, the shift coinciding with the emergence of a reflective tail shimmering in sunlight. Around its core, a growing haze of dust and vapor concealed the very oscillations scientists hoped to decode, obscuring its spin and distorting its light. As debates deepened, new Atlas data began to flow in a spectral record of how its color and brightness evolved over months, promising to reveal whether this cosmic traveler is merely misbehaving or rewriting what we thought we knew about interstellar visitors. The data stream from the Atlas survey, captured between the 28th of March and the 29th of August, 2025, presents a chromatic timeline of profound intrigue. As the interstellar object designated 3I Atlas journeyed sunward, its reflected light began to tell a story written not in words, but in shifting wavelengths and fluctuating luminosity. The photometric multiband observations reveal a clear, yet deeply anomalous trend. The object's spectrum systematically drifted towards the blue, its color index changing in a manner that defied simple cometary outgassing. Models, the absolute brightness, denoted as H of T, did not follow a predictable, linear decay, but exhibited a complex, almost hesitant diminution. This was not the steady brightening of a simple, inert body warming under the solar furnace. What physical process could orchestrate such a symphony of light and color, a composition that seemed to rewrite its score as the conductor drew nearer? From a conventional standpoint, one might attribute this spectral bluing to a change in the surface composition or the particle size distribution within a nascent coma. As 3I Atlas approached the Sun, solar heating could have triggered the sublimation of volatile ices, increasing the proportion of finer, submicron ice crystals in the dust cloud. These smaller particles scatter blue light more efficiently through Rayleigh or Mie scattering mechanisms, much like the Earth's atmosphere, leading to an observed color shift. The non-linear decay in h of t could then be interpreted as episodic outbursts, where sudden jets of gas and dust temporarily enhance the object's reflectivity before it settles back to a quieter state. This is the narrative of active comets, a story we have told ourselves for centuries based on our own solar system's wanderers. Yet, does this familiar tale truly account for the precision of the color shift and its early onset, while the object was still remarkably distant, beyond 4 astronomical units? The data, when compared with earlier sightings from the Zwicky Transient Facility and Pan-STARRS, introduces a critical anomaly. The color transition began significantly earlier than any conventional thermal model would predict for a body of water ice or carbon monoxide. Furthermore, the correlation between the object's color and its brightness was found to be phase angle dependent, a subtlety that suggests a highly structured and directional scattering surface, not an isotropic cloud of gas and dust. This leads us to a more speculative hypothesis. Perhaps we are not observing simple outgassing, but a form of photonic engineering. The object's mantle could be composed of what we might term optical dual-state particles, microscopic structures, featuring a dark, dusty core encased within a transparent shell of crystalline ice. As thermal energy from the sun penetrates this shell, it could induce a phase transition in the ice or a reorientation of the core, effectively flipping a photonic switch that alters the particle's reflectivity and scattering properties across different wavelengths. Could a natural process craft such sophisticated optical elements, or are we witnessing the principles of metamaterials on an interstellar scale? This line of inquiry compels us to consider increasingly profound interpretations. At a moderate level, the spectral changes could be driven by a simple increase in the ratio of pristine ice grains to carbonaceous dust, a natural filtration process as weaker material is shed. A stronger hypothesis posits a shell-shedding mechanism, where the intense thermal gradient systematically strips away a dark, refractory crust to reveal a brighter, icy subsurface layer, a form of cosmic exfoliation. But the most extreme and most captivating proposition is that of a surface or near-surface material capable of selective, wavelength-dependent reflection. This material could be composed of naturally occurring or artificially structured nanoparticles that resonate at specific frequencies. The daily and nightly thermal cycles on the object's rotating core could drive a cyclical reconfiguration of these particles, creating the observed periodic color deviations. This would not be mere geology, it would be a form of photonic climatology, a daily rhythm of light and color dictated by the object's very structure. If this is the case, then what other luminous secrets might its rotation be hiding? The opportunity presented by 3I Atlas is unparalleled, a chance to fundamentally recalibrate our phase color models for interstellar objects, to build a new astrophysics from a single, enigmatic data set. The risk, however, is equally significant. If we persist in interpreting its behavior through the lens of typical cometary activity, we will profoundly misjudge its dust production rates and evolutionary trajectory. Our subsequent observation campaigns, designed around flawed assumptions, could fail to capture the most critical phases of its transformation. This forces us to look backward, to search for its origins in our archival data, to understand the moment it first stirred from its deep space slumber. And if its activity began not at the snowline of our system, but far earlier, in the cold darkness beyond the giant planets, what would that imply about the nature of its journey and the environment from which it came? Perhaps the initial whispers of its awakening were already captured, silently waiting in the data of another great sentinel, one that stares not at a single point, but at vast swathes of the cosmos. The void beyond the orbit of Jupiter is a place of profound stillness and cold, a realm where most comets exist as little more than inert, primordial ice. Yet, in the months of May and June 2025, the transiting Exoplanet Survey satellite a sentinel designed to seek out worlds orbiting distant suns, recorded a faint and curious glimmer from an object, then catalogued as a simple minor body. This was our first, almost imperceptible, indication that the entity later designated 3I Atlas was stirring from its slumber at a staggering distance of 6.4 astronomical units, a place where solar warmth is but a feeble whisper. The data revealed not a steady beacon, but a subtle fluctuating light, a rhythmic pulsation of brightness that defied the inert darkness expected at such a frigid remove from the Sunday. According to current models, a comet at this distance should be locked in a deep cryogenic sleep, its volatile ices, carbon monoxide, and carbon dioxide still frozen solid. The faint outgassing needed to produce such a light curve could, perhaps, be explained by a subsurface reservoir of particularly volatile carbon dioxide, beginning its slow sublimation under an unthinkably weak solar influence. But what if the trigger was not external, but internal? What if this was not a passive warming but an active awakening? This leads us to a more speculative hypothesis. Could the core of 3I Atlas be threaded with a network of intricate heat conduits, functioning like a geothermal system? These theoretical structures, if they exist, might have been activated not by the distant sun, but by the decay of exotic radioactive isotopes embedded within the comet's matrix, isotopes not native to our own solar system. This would be a remnant signature, a physical artifact from the interstellar cloud from which this traveller originated. The evidence, when meticulously pieced together, lends a degree of credence to this extraordinary notion. Advanced stacking techniques applied to the TESS imagery confirmed a gradually intensifying signal, a light curve that aligns precisely with the sublimation temperatures of carbon dioxide and even formaldehyde at these extreme distances. Simultaneously, and perhaps most compellingly, several ground-based photometric campaigns reported small amplitude variations in the object's brightness, variations that were in phase with the TESS data. This independent confirmation suggests a low-level, yet persistent, activity originating from the body itself. Is it mere coincidence, or are we witnessing the first faint heartbeat of an object with an internal energy source? We must therefore analyze this premature activity through a series of escalating interpretations. The most conservative, or level 1, explanation posits a simple compositional anomaly, a nucleus unusually rich in carbon dioxide, which possesses a higher volatility than water ice, thus allowing it to sublimate under minimal thermal provocation. This is a plausible, if remarkable, scenario. A level 2 interpretation, however, introduces a more dynamic mechanism. Intense thermal stresses, induced by the object's first encounter with even trace amounts of stellar energy, could have fractured deep-seated icy caverns within the nucleus. These fractures would expose fresh, volatile ice to the vacuum of space, creating weak, localized jets, the first, faint breath of a comet beginning to awaken from within. But what if the truth is far more extreme? A level 3 hypothesis ventures into the realm of the truly exotic. It suggests the core of 3I Atlas contains a phase of supervolatile ice, a metastable solid that undergoes a form of chain reaction evaporation when triggered by a specific, minuscule energy threshold, a threshold that may have been crossed by the decay of a single radioactive atom from another star. Could the faint light we detected have been the visible echo of a microscopic interstellar domino effect? The profound opportunity presented by this remote observation lies in its power to infer the very activation energy of this unknown material. By monitoring the precise conditions under which 3I Atlas first began to stir, we can calculate the latent properties of its substance from across the gulf of space. This data is not merely academic, it is the essential precursor, the guiding beacon for a sample return flyby mission that could be launched within the next decade. To touch this object, to bring a piece of it back to Earth, would be to hold a fragment of another stellar system in our hands. But as we prepare for such an encounter, a new and equally puzzling transformation begins to manifest, a change not in brightness, but in color, heralding the next stage of its mysterious evolution. For as its activity intensified, its deep red hue began to fade, shifting towards the neutral white of our own sun, a transformation that coincided with the emergence of a distinct, reflective dust tail. What could this chromatic shift reveal about the true nature of the materials now being exposed to the light? As the interstellar object 3I Atlas continued its solitary journey, a profound and visible metamorphosis began to unfold. The object, initially characterized by a distinct reddish hue, began to shed its crimson cloak, its color shifting steadily towards the neutral spectrum of our own Sunday. This chromatic evolution was not merely an aesthetic change, it was a direct communication from the object's evolving coma, a clear signal that reflective ice was gaining dominance over the darker, complex organics that had first defined its appearance. The GR and RI color indices, meticulously measured throughout the months of May to August 2025, charted this undeniable decline in redness. The most compelling visual evidence arrived with deep field imagery, which revealed a nascent, brilliantly reflective tail beginning to separate from the darker, dust-dominated plume. This was the birth of a reflection tail, a structure whose very existence demanded an explanation for the sudden preponderance of highly efficient scatterers of light. Could a simple outgassing of fresh, fine water ice grains from a newly active region fully account for such a dramatic and systematic color shift? According to current cometry models, the exposure of pristine water ice to solar radiation can indeed produce a surge in neutral scattering particles. The observed slight increase in polarization at intermediate phase angles would be consistent with the presence of such fine, smooth grains. This mainstream interpretation posits that as 3I Atlas ventured closer to the Sun, subsurface volatiles were activated, ejecting a new population of bright, microscopic ice crystals into the coma, thereby diluting the redness imparted by the earlier, dustier outgassing. The laws of physics, as we understand them, provide a complete and rational framework for this process. Yet, one must ponder if this model is sufficient. The speed and efficiency of the color transition and the sheer brilliance of the reflection tail suggest a population of scatterers that are almost perfectly optimized for their purpose. Does the random ejection of fine grains truly lead to such a potent and coherent reflective structure? This leads us to a more speculative hypothesis. Perhaps the particles comprising the reflection tail are not merely fine, but are engineered by the very forces of deep space. We might envision these as mirror ice particles, crystals of water ice, whose molecular structure has been subtly altered over its long interstellar voyage. Subjected to the constant, gentle pressure of stellar radiation across light years, these crystals could have developed facets with an extraordinary degree of flatness. Furthermore, the radiation pressure itself, a force we routinely use to model the dynamics of dust in cometary comae, could be acting as a cosmic selector. It may not merely be pushing particles away, but actively sorting them, aligning these flat, plate-like crystals to present their broadest, most reflective faces perpendicular to the direction of the sunlight, like a vast, dispersed fleet of solar sails. What natural process could refine a cloud of dust and ice into a coordinated, light-maximizing array? We can analyze this phenomenon through a cascade of increasingly bold inferences. At its most conservative level, the color change is a straightforward addition of fine ice grains to the coma, a simple supplement to the existing particle distribution. A stronger interpretation, however, suggests a radical restructuring of the particle size distribution itself, where radiation pressure acts as a discriminating filter, systematically ejecting smaller, darker grains while retaining and orienting larger, brighter, and more specularly reflective ice flakes in the inner coma. But what if the truth is more extreme? We must entertain the concept of optical snow, a surface crystallization process not seen within our own solar system. Imagine the nucleus of 3I Atlas, under increasing solar warmth, not merely ejecting grains, but undergoing a phase transition on its surface, growing vast, contiguous sheets of crystalline ice. These plates, acting like colossal, kilometers-wide mirrors, could reflect sunlight with an efficiency that would instantly neutralize the object's color index. Is the nucleus we are observing not a rubble pile, but a sculpture of light, sheathing itself in a temporary armor of perfect reflection? The positive consequence of this shift to a neutral spectrum is a rare opportunity for planetary astronomers. The simplified scattering properties allow us to peer past the veil of color and more accurately reverse engineer the particle size distribution within the reflection tail. The data streaming from the James Webb Space Telescope and ground-based observatories like the VLT can now be fed into refined models, improving our simulations of reflection tails for all interstellar objects we may encounter in the future. We are, in effect, being handed a calibrated tool to understand the fundamental building blocks of cometary activity beyond our Sunday. But if the particles are indeed aligning, if a form of cosmic phototaxis is at play, what does this imply for the internal structure, and even the origin of the object itself? This precise and deliberate seeming change in color, this shedding of a red identity for a neutral one, forces us to look closer, to measure not just what light is reflected, but how it is changing over time. For the light curve of 3I Atlas holds another, more subtle secret, a rhythmic flicker that hints at the very mechanics of its disintegration. As the object drew nearer to the Sun, the rate at which its brightness faded began to change, not once, but in two distinct phases, suggesting a fundamental shift in the very mechanism, dispersing its dust and ice. What physical transformation, hidden within the heart of this visitor, could account for this dual-paced dimming? The light curve of an object in the void is its heartbeat, a rhythmic pulse that speaks of its rotation, its composition, and its very nature. For Comet 3I Atlas, this pulse was expected to follow a predictable, linear decay, a gentle slope downward as its initial, volatile-rich outburst subsided. Yet, the data tells a different story. The slope coefficient, denoted as 8, did not hold its promise of linearity. In the months spanning April to August 2025, the comet's light curve changed its rhythm, as if the engine of its dust production had shifted into a different gear. The initial, more gradual decline in brightness gave way to a steeper, more precipitous drop. This inflection point, this break in the slope, is more than a statistical anomaly. It is a signature of a fundamental change occurring deep within the object. What internal clock, then, governs this sudden shift in tempo? According to current models of cometary behavior, such a break in the light curve slope can be attributed to a transition in the dominant sublimation process. Initially, the object may have been outgassing highly volatile ices from its surface, producing a large, optically thick dust coma that scattered sunlight efficiently, leading to a slower rate of brightness change. As these surface ices were depleted, the activity could have shifted to a different volatile, perhaps water ice, sublimating from beneath a thinning crust, resulting in a different dust grain size distribution and a steeper photometric slope. This is a logical progression, a narrative of sequential depletion that fits within the established laws of physics. Yet, when we cross-reference this photometric break with the object's rotational phase, a complication arises. The change does not correlate perfectly with a simple geometric viewing angle. It appears to be an intrinsic shift in the scattering mechanism itself. If the cause were merely the exhaustion of one ice and the initiation of another, why would the transition be so sharply defined in the data, and why would it resist a purely geometric explanation? This resistance to conventional interpretation invites a more speculative hypothesis. Perhaps within the core of 3I Atlas exists a seasonal zone, a region of material that undergoes periodic phase transitions synchronized with its rotation. Imagine a structure not of uniform composition, but of layered strata with varying thermal conductivities and volatile contents. As the object spins, different longitudinal bands are exposed to the weak solar radiation. A specific region, rich in a particular type of ice, might only become active when it faces the sun, its subsurface temperature crossing a critical threshold. The observed break in HT would then mark the moment this seasonal band rotated into its active phase, dramatically altering the overall dust production and its scattering properties. The light curve, in this view, is not just a measure of total output, but a map of active geological provinces on a rotating world. But what kind of internal architecture could sustain such starkly differentiated and clockwork-precise active regions? The evidence from the two distinct slope phases, the slower outer phase and the steeper inner phase, demands a deeper analysis, a tiered inference into the possible mechanisms at play. At the most conservative level, we can posit a simple transition from surface dust scattering to the sublimation of subsurface ices. As the loose, unconsolidated dust mantle is blown away by initial outgassing, it exposes more resilient, ice-cemented layers beneath. The subsequent sublimation of this interstitial ice could liberate dust grains more efficiently, leading to a higher production rate of smaller particles that scatter light differently, accounting for the steeper slope. This is a minimal, almost expected, evolutionary step for a comet. Yet, does this gentle transition fully capture the potential for sudden structural change? A stronger hypothesis suggests a more violent restructuring of the surface. The intense thermal stress from repeated solar passages could have caused a network of fractures to propagate deep into the nucleus, tearing open concentrated vent channels. These fissures would act as nozzles, focusing the outflow of gas and dust into collimated jets. The transition in height would then correspond to the moment these plumbing systems became fully established, bypassing the diffuse surface emission and creating a few highly efficient point sources of activity. The change in the light curve slope is not merely a change in composition, but a change in the very geometry of outgassing from a broad, gentle breeze to a focused, powerful geyser. What forces, then, would be required to shatter the interior of a small world in such a deliberate manner? The most extreme, yet logically consistent interpretation is that of a localized collapse. A large section of the crust, weakened by subsurface sublimation and thermal fatigue, could have catastrophically failed, carving away to expose a fresh, intensely active interior. This newly revealed surface would be rich in pristine volatiles, leading to a sudden, massive surge in outgassing. In this scenario, the steepening of height is not a sign of decay, but of a brilliant, transient exposure of the object's luminous core. The light curve records a moment of geological violence, a small-scale disintegration that temporarily makes the object appear far brighter and its decline far more rapid. This would be a singular event, a punctuation mark in the object's long history of quiet drift. But if such an event can occur once, what prevents it from happening again, with even greater consequence? This leads us directly to the risk assessment, a necessary caution born from these observations. If the observed slope break is a precursor to further internal instability, and if this process continues to propagate into the object's inner regions as it approaches its perihelion, the risk of a post-perihelion disintegration event increases significantly. Such a fragmentation would not only represent the end of this particular scientific subject, but would also pose a challenge to the observational strategies of our most powerful telescopes. The safe observation protocols for large instruments like the James Webb Space Telescope are designed around predictable targets. A large-scale disintegration could release a cloud of high-velocity dust particles, creating a navigational hazard for spacecraft and potentially damaging sensitive optics if pointed too closely. The changing slope of a light curve thus transforms from an abstract photometric parameter into a direct warning signal. Are we monitoring these celestial visitors closely enough to anticipate not just their scientific revelations, but their potential for sudden, destructive transformation? Yet, all these interpretations, from the gentle to the catastrophic, rely on our ability to see the true signal from the nucleus. We have been discussing the light curve as if it were a pure, unadulterated measure of the core's activity. This is, of course, a simplification. The very coma whose dust production we are measuring acts as a veil, a dynamic and opaque shroud that obscures the subtle photometric variations originating from the rotating nucleus. The heartbeat we seek to measure is filtered through a turbulent, ever-changing atmosphere of its own creation. How much of the signal we attribute to the nucleus is, in fact, a phantom of the obscuring coma? The coma, that vast and tenuous atmosphere of gas and dust enveloping the nucleus, is our first and greatest obstacle to perceiving the true nature of the object at the heart of this mystery. It presents itself as a luminous veil, a DA, beautiful but deceptive shroud that both reveals the comet's presence and conceals its most fundamental secrets. To the photometer, the instrument designed to measure the faint whisper of light from the core, the coma is not a neutral medium, but a dynamic, scattering fog. It acts as a cosmic diffuser, smoothing out the sharp, periodic fluctuations in brightness that would betray the rotation of the solid nucleus. The very heartbeat of the object is muted, its rhythmic pulse absorbed and scattered by billions of dust particles and gas molecules, leaving behind a light curve that is frustratingly dampened, an echo of the true cadence within. We are attempting to listen to a symphony playing in a sealed room, our ears pressed against the outer wall, hearing only the muffled, indistinct bass notes. Could it be that the simple, physical presence of this coma is the sole architect of the observational challenge we face? According to current models of cometary physics, the coma is a roughly spherical cloud, its density decreasing predictably with distance from the nucleus. The attenuation of the light curve amplitude is a straightforward consequence of this geometry. As the comet approached the Sun throughout the latter half of 2025, the coma expanded and thickened, effectively diluting the signal from the rotating core. The observed gradual decrease in the amplitude of the light variation from May to August aligns perfectly with this expectation. It is a classic case of signal-to-noise degradation, where the noise is the constant, unchanging glow of the coma itself, slowly drowning out the periodic signal we seek. The mainstream explanation is one of pure optics, a problem of contrast. But does a simple, homogeneous cloud of dust fully account for the specific, nuanced distortions we are recording? The data, however, hints at a more complex reality. When we analyze light curves filtered through different aperture sizes, a technique akin to observing the object through a series of concentric portholes, we do not find a consistent signal. The phased light curves, the graphs we use to pinpoint the rotation period, shift and slide against one another. A peak in brightness detected through a small aperture does not perfectly align with a peak seen through a larger one that captures more of the coma's light. This phase discrepancy suggests that the coma is not a uniform shroud, it possesses structure. Long exposure images reveal faint, radial jets, delicate streamers of material being actively ejected from the nucleus. These are not static features, they rotate with the core, sweeping across our line of sight like celestial lighthouse beams. What if the coma is not merely a passive fog but possesses its own dynamic weather, density waves, and swirling eddies that drift around the nucleus, creating their own rhythmic, if subtle, pulsations in the integrated light? Could the faint, variable flickering we attribute to the nucleus actually be the shadow play of these transient atmospheric features? This leads us to a more potent hypothesis. The first level of interpretation is the gentle one, signal dilution. The second, stronger level, proposes that we are not just measuring a dampened signal, but a false one. The transient passage of a bright jet or a dense cloud of icy grains through the photometer's field of view could itself generate a periodic or quasi-periodic variation in brightness. The 16.16-hour periodicity, so tantalizingly close to confirmation, could be a phantom rhythm born from the repetitive geometry of these jet crossings, a harmonic of the coma's activity rather than a direct measurement of the nucleus's spin. We are then faced with a profound uncertainty. Are we timing the rotation of a solid body or the cadence of its atmospheric expulsion? But we must consider a third, more extreme possibility. What if the obscuration is not a passive or randomly structured phenomenon? The consistent damping of the amplitude, the phase shifts, the entanglement of jet light with core light, could these effects be compounded by a self-regulating veil? A hypothetical mechanism, perhaps governed by the very laws of solar heating and outgassing we are only beginning to understand, that actively maintains a certain opacity around the nucleus. A feedback loop where increased solar radiation triggers more outgassing, which in turn thickens the coma precisely enough to protect the nucleus's rotational signature from being easily decoded. This would render all efforts to measure a true period from simple integrated photometry utterly futile. Every attempt to peer through the veil would only cause the veil to thicken in response. Is the coma merely a cloud, or could it function as a dynamic shield, intelligently obscuring the truth at the object's core? This profound challenge, however, is not an end but a beginning. It forces a technological and methodological evolution. The solution lies not in more powerful telescopes, but in smarter ways of seeing. This dilemma is the very catalyst driving the development of advanced point spread function and coma deblending algorithms, sophisticated software designed to computationally separate the light of the point-like nucleus from the glow of the extended coma. Furthermore, it necessitates a shift towards spatio-temporal photometry, where light is not just collected, but tagged with its precise location of origin on the comet's surface and its time of arrival. We must move from listening at the wall to developing a sonogram that can visualize the internal structure of the room itself. Can we engineer a new form of perception, one capable of dissecting this luminous fog and isolating the solitary heartbeat at its center? The relentless pursuit of this hidden rhythm has, against all odds, yielded a candidate. From the noise, from the obfuscating glow of the coma, one research group has extracted a precise number, a rotation period of 16.16 hours. This figure now hangs in the balance, a tantalizing prize pulled from the depths of a turbulent sea of data. It is a testament to human ingenuity, a potential key to unlocking the object's history and physical properties. But in the rigorous world of science, a single result is merely the opening statement in a debate. The declaration of a 16.16-hour period has not settled the matter. It has, instead, ignited the very controversy it sought to extinguish. For every colleague who sees a clear signal in their analysis, another sees only an artifact, a pattern coaxed from chaos by overzealous data processing and the relentless, deceptive influence of the coma. The question is no longer just about the period itself, but about the standards of proof we require when observing such a profoundly obscured object. If we cannot trust the light, what can we trust? The pulse was detected, a faint but persistent rhythm emerging from the chaotic light curve. A rotation period of approximately 16.16 hours. To some, this number appeared with the reassuring constancy of a cosmic heartbeat, a fundamental parameter revealing the object's spin. According to current models, such a period is well within the expected range for a cometary nucleus of a certain size, its rotation governed by the conservation of angular momentum from the primordial cloud. The observed light variation, a fluctuation of approximately 0.3 magnitudes, could be neatly explained by an irregular, elongated nucleus. Its uneven surface reflectivity and cross-section presenting a changing face to our telescopes as it spins, a simple, well-understood phenomenon. The data, published by a dedicated team in the summer of 2025, was presented as a clear signal extracted from the noise, a key unlocked. But is a key that fits so neatly into an existing lock truly revealing a new chamber, or merely confirming the architecture of the one we already inhabit? Could this 16.16-hour rhythm be nothing more than an echo in the swirling fog of its own coma? The mainstream interpretation offers a solid foundation. Scientists suggest this could be due to a single monolithic core, its rotation unperturbed and stable over the observational time frame. The measured period and the modest light curve amplitude would then allow us to constrain its shape, to estimate its axial ratio. It is a clean, elegant solution, one that aligns with our understanding of countless other small bodies in our solar system. The very normality of the finding is, in a way, its greatest strength. Yet, that very normality is what gives other researchers pause. The signal-to-noise ratio was low, they argue, the data plagued by the comet's own activity. The ever-shifting coma, a veil of dust and gas, can itself introduce periodic brightening and dimming, a phantom rhythm that mimics rotation. Furthermore, the observational schedule, bound by the terrestrial cycle of day and night, creates a powerful alias, a one-day beat that can interfere with and distort the true signal. Could the 16.16-hour period be a mirage, a mathematical phantom born from the interplay of a different, true period and the gaps in our earthly vigil? This skepticism births a more speculative hypothesis. Perhaps the core is not a single body, but a binary system locked in a tidal embrace, a dual-core configuration. In this scenario, two distinct fragments, orbiting a common barycenter, could produce a complex light curve. The primary rotation of one or both bodies, combined with their orbital dance, might generate a beat frequency, a composite signal that manifests as the observed 16.16-hour period. The slight amplitude modulation noted in the data could be the telltale signature of this celestial waltz, a subtle clue to a deeper structural complexity. This would explain why the polarimetric time series data failed to show a corresponding, clear modulation. The polarization of light is sensitive to the fine dust in the coma, which might not perfectly trace the intricate gravitational choreography of a hidden binary nucleus. What if we are not listening to the spin of a lone world, but to the synchronized ticking of a dual clock system, its true mechanism obscured by its very harmony? The debate forces a tripartite analysis, a stratification of possibilities that range from the conservative to the extreme. At the first, most lenient level, the period is real, but its amplitude is compressed. The 0.3 magnitude variation is not a true representation of the nucleus's asymmetry, but a dampened one, its signal softened and blurred by a persistent, optically thick dust shroud. The core could be wildly irregular, but we see only a muted ghost of its true rotation. Is the universe showing us a faint echo, or are we merely hearing it through a wall? At the second, more forceful level, the period itself is an illusion. It is an alias, a phantom frequency generated when the comet's true, unknown rotation period mixes with the 24-hour cadence of our observations from a single hemisphere. The 16.16-hour value is a numerical artifact, a siren song leading us away from the true temporal nature of the object. How can we be certain we are measuring the rhythm of the heavens and not the rhythm of our own planet? Then, there is the third, most extreme tier of interpretation. It posits that there is no single, stable period at all. The nucleus may not be in a simple rotation, but in a state of precession, its spin axis itself slowly wobbling through space, creating a complex, evolving light curve that we have only sampled a fraction of. Or, more radically, the body could be in a state of rotational chaos, its spin perturbed by outgassing torques, on the verge of fragmentation, or excited into a tumbling mode. The signal we have captured would then be merely a transient snapshot of a disintegrating clock, a fleeting moment of apparent order in a cascade towards dynamical entropy. What if the object is not a timekeeper, but a timepiece shattering in slow motion, and we have mistaken the vibration of a single spring for the steady tick of a functional mechanism? This profound disagreement, this clash between the straightforward and the deeply complex, has yielded an unexpected consequence. It has compelled the global astronomical community to evolve its methodology. The only way to break the deadlock is to achieve a continuous 24-hour vigil to defeat the aliasing demon of the single observatory night. A coordinated global relay has been proposed, a network of telescopes spanning the longitudes, passing the watch from Chile to the Canary Islands to Hawaii and onward. This object, this faint and speeding puzzle, has become the catalyst for a new model of collaboration, a practice run for the next generation of fast-moving, ephemeral targets that will undoubtedly be discovered. Has the ambiguity of a single comet's rotation forced upon us the necessity to become a truly global sensor, a unified eye upon the cosmos? This relentless pursuit of its rhythm inevitably draws our focus to the other half of the equation, the subtle dance of its brightness, the faint whisper of its 0.3 magnitude variation. For within that small number lies a story not of time, but of form, a cryptic message about the object's very shape and structure. The observed light variation of approximately 0.3 magnitudes is a subtle but persistent whisper in the dataset, a quiet signature etched against the backdrop of interstellar space. This specific amplitude is far from the dramatic swings indicative of a tumbling irregular shard. Instead, it suggests an object that is not perfectly spherical, yet not wildly asymmetric. The natural conclusion, drawn from centuries of asteroid studies, is a body gently rotating, its elongated or slightly misshapen form presenting a continuously changing cross-section to our telescopes. A prolate spheroid, perhaps, or a body with significant surface relief, would produce just such a gentle, rhythmic pulsation in brightness. The mathematics of light curves have long been refined to interpret these celestial rhythms, translating a graph of luminosity into a probable shape. But is the language of simple geometry sufficient to describe a messenger from another star? This leads us to a more speculative hypothesis. What if this consistent variation is not a product of a simple, solid ellipsoid, but of an object with a radically different internal architecture? Imagine a core, not of solid rock, but of a porous, frothy structure, a cosmic pumice stone, riddled with caverns and vesicles. Within this fragile matrix, pockets of volatile ices could be trapped. As this rubble foam rotates, different facets come into view. One hemisphere might present a relatively solid, unreflective crust, while the opposite could be a labyrinthine network of open pores and exposed ice patches, creating a stark contrast in albedo. The 0.3 magnitude variation could then be the heartbeat of this fragile structure, the regular alternation between a consolidated face and a fractured, volatile, rich one. Could the true nature of this traveller be not a monolithic stone, but a delicate, frothy whisper of a world? The empirical evidence begins to narrow the possibilities. The consistency of the amplitude, even when observed through smaller apertures that minimize the distorting effects of optical coma, argues against the signal being an artifact of our instrumentation. Furthermore, a slight but measurable increase in the amplitude at larger phase angles, when the object is seen more from the side, is a classic indicator of surface roughness, as shadows are elongated and enhanced. Most tellingly, the color of the object does not modulate strongly in lockstep with the light curve. If the brightness changes were due to transient outgassing events, one would expect significant color shifts as the composition of the surrounding coma changed. The absence of such chromatic variation points decisively away from volatile-driven activity and firmly toward a geometric cause, a shape-driven signal. But what specific geometry could produce such a clean, repeating signature? We can now embark on a tiered analysis, a hierarchy of interpretations with increasingly profound implications. The first, and most conservative, level posits a moderately elongated core, a shape akin to a spindle. This is a simple, elegant solution that fits the data without invoking exotic physics or unknown materials. The rotation of a cigar-shaped object would naturally produce the observed sinusoidal light curve. It is the default assumption, the null hypothesis that must be disproven. Yet, does the simplicity of this model belie a more complex underlying reality? The second, more assertive level of interpretation suggests a more complex morphology. Perhaps we are not observing a simple elongation, but a contact binary, two distinct lobes in a gentle, permanent embrace. The light curve of such a configuration, a cosmic dumbbell, would be characterized by a double-peaked pattern, a subtle nuance that our current data may not yet have the resolution to fully decompose. Alternatively, the object could possess a Bactrian camel profile, with two major albedo features or topographic highs that dominate its reflective properties. As it turns, these two humps would sequentially face the Earth, creating the observed variation. This already challenges our understanding of planetesimal formation, suggesting that the processes that build small bodies are universal, operating even in the vast voids between stars. But what if the truth is stranger still? The third, most extreme interpretation pushes the boundaries of material science. What if this object is not a binary, but a swarm? A loose aggregation of numerous smaller fragments, each with its own distinct albedo and composition, held together by the faintest of gravitational ties or by weak van der Waals forces. This rubble pile model, applied to an interstellar object, would be revolutionary. The observed light curve would then be a complex symphony of individual reflections, a composite signal from a cloud of shards flying in loose formation. The consistent 0.3 magnitude variation would be an emergent property of this chaotic system, an average struck from the flickering of 1,000 tiny mirrors. This presents a profound puzzle of orbital mechanics and material strength. How could such a tenuous structure survive the immense journey through interstellar space, buffeted by galactic tides and traversing radiation fields? What does its continued existence tell us about the mechanical durability, or perhaps the internal tensile forces, at play within these exotic visitors? This meticulous analysis of a single parameter, a gentle flux of photons varying by a precise amount, thus opens a direct window into the physical characteristics of the object. From this light curve, we can begin to infer the probable axial ratio, to map the large-scale topography, and to estimate the surface roughness. These are not mere abstract numbers, they are critical inputs for models that seek to understand the very cohesion of this body. The mechanical strength required to hold a spinning, elongated object together, or to maintain the integrity of a contact binary, is substantially higher than that of a loose rubble pile. The light curve, therefore, becomes a remote probe of the object's internal structure and its history of formation. But if the shape is the sculptor of the light, what then is the sculptor of the color, and how do the two interact to create the final, observed spectrum? This inevitably draws our attention to the coma, the faint, ephemeral atmosphere that some of these objects exhibit. The light we receive is not solely from the nucleus. It is a blended signal, a combination of reflected sunlight from the core and scattered light from the surrounding cloud of particles. To truly understand the nucleus, we must first disentangle its light from that of its own halo. This requires a forensic analysis of the spectrum, a search for the spectral fingerprints that distinguish one type of particle from another. The observed brightness at any given moment is thus a delicate balance, a sum of contributions from various components, each with its own story to tell. But how do we separate the whisper of dust from the gleam of ice within the coma's diffuse glow? The key lies in the subtle, yet critical distinction between a dust spectrum and an ice spectrum. Dust, composed primarily of silicates and carbonaceous compounds, tends to scatter light in a relatively featureless, reddened continuum. Its spectral signature is often a smooth slope, telling us little beyond its general composition and size distribution. Ice, however, is a more articulate substance. Water ice, carbon dioxide ice, carbon monoxide ice, each possesses distinct absorption features at specific infrared wavelengths, deep troughs in the spectrum that act as definitive identifiers. A coma rich in icy grains will therefore imprint a specific, recognizable pattern onto the reflected sunlight, a pattern that the James Webb Space Telescope is exquisitely designed to detect. The ratio of dust to ice, however, is unlikely to be a constant. Could transient surges in sublimation or the rotational presentation of different volatile-rich terrains on the nucleus cause this ratio to fluctuate, and in doing so, introduce its own independent modulation into the object's light curve? Within the faint, shimmering veil of a comet's coma, a silent cosmic duet unfolds. Two distinct voices, one of dust and one of ice, rise and fall in a complex harmony, their interplay directly transcribed onto the shifting line of the comet's light curve. The dark, carbonaceous dust sings a low, resonant baritone, absorbing sunlight with a broad, featureless spectrum, while the brilliant, volatile ice delivers a clear, sharp soprano, scattering light with a spectral signature rich in the telltale features of water and carbon dioxide. The observed light curve is but the final mixed recording of this performance, a dynamic and ever-changing composition. According to current models, the relative amplitude of these two voices is governed by solar heating, which dictates the sublimation rate of ices and the subsequent liberation of dust grains from the nucleus. The initial, gentle warming at great distances should favor the release of more volatile, pristine ices, while closer proximity to the Sun activates water ice and unleashes the darker, refractory dust locked within. This predictable sequence forms the basis of our understanding of cometary activity. Yet, what if the performers themselves are not merely simple grains of dust or pure crystals of ice, but are instead complex, composite entities whose very nature can transform in an instant under the solar spotlight? The conventional explanation for shifts in a comet's color and polarization hinges on changes in the particle size distribution and composition within the coma. Scientists suggest that a redder color index indicates a preponderance of larger, rougher dust grains, while a bluer hue points to a finer, ice-dominated spray. Observations of negative polarization at small phase angles further support this, as this phenomenon is strongly associated with fine, transparent particles, like icy grains, which undergo single scattering within their volumes. The continuous scattering spectra we obtain are thus interpreted as a real-time census of the dust-to-ice ratio. A comet's light curve, particularly in the blue filters, is notoriously more volatile than in the red, as the blue signal is exquisitely sensitive to the sudden injection of fresh, small ice crystals into the line of sight. This framework provides a rational, if intricate, picture of cometary outgassing. But does this granular model possess the resolution to explain a light curve that fractures and reconstitutes itself over the span of a single earthly night? A more speculative hypothesis proposes the existence of a chimeric particle, a dark, organic-rich core sheathed in a mantle of water ice. These dark core, ice mantle grains would, for a time, present the spectral characteristics of ice. Their fate, however, is tied to a precise thermal trigger. As the comet rotates, a sudden pulse of solar heat, focused on a freshly exposed jet, might not merely sublimate the surface of these grains, but violently strip the icy mantle away entirely. In a matter of hours, the same population of particles would undergo a spectral metamorphosis, flipping from a bright, scattering ensemble to a dark, absorbing one. The light curve would not merely brighten or dim, it would fundamentally alter its character, as if the orchestra had abruptly switched instruments mid-symphony. The observed fluctuations in the color index and the strengthening of negative polarization during episodes of fine particle ejection could be the direct signature of this mantle-shedding process. Could it be that we are not watching simple sublimation, but a far more dramatic and particulate form of metamorphosis? To comprehend the full implications, we must analyze this phenomenon across three escalating tiers of intensity. The first, a gentle fluctuation, corresponds to the normal weather of the coma. Minor amplitude variations in the light curve are the result of diurnal cycles on the nucleus, as different terrains, rich in either dust or ice, rotate in and out of sunlight. This is the comet breathing, a slow and rhythmic exchange between its two primary components. The data shows these small-scale oscillations in the dust-to-ice ratio, a testament to the heterogeneous nature of the cometary surface. But are these gentle breaths merely masking the prelude to a far more forceful exhalation? The second, stronger tier manifests as a frostwash event. Here, a powerful, localized outburst, perhaps triggered by the collapse of an overhanging cliff or the penetration of heat into a sealed pocket, releases a concentrated wave of superheated vapor. This vapor stream does not just carry dust, it scours the immediate area, liberating and propelling a vast quantity of pristine ice grains. The light curve responds with a sharp, short-term brightening, particularly acute in blue wavelengths, accompanied by a dramatic bluewood shift in the color index and a spike in negative polarization. The coma, for a brief period, becomes dominated by the brilliant soprano of ice. Yet, what physical limit exists to prevent such a process from achieving a state of transformative extremity? The third, most extreme tier, envisions a temporary phase change of monumental consequence. Within the dense, cooling plume of a massive outburst, the conditions might be right for a rapid recondensation of vapor. Water molecules, ejected violently into the vacuum, could almost instantaneously renucleate onto the surfaces of existing dust grains, not as frost, but as smooth, glassy coatings. These temporary mirror grains would possess an albedo far exceeding that of normal frosted ice. For a fleeting period, the entire coma could be transformed into a phenomenal scattering surface, causing the comet's brightness to surge in a way that defies all predictions based on simple surface area. The albedo of the coma itself would be temporarily and radically altered. Is the ultimate key to some of the most violent cometary outbursts in history not the quantity of material released, but a transient, alchemical quality imposed upon it? The practical application of this duality is immediate and profound for the observation of interstellar interlopers. To deconvolve the real-time contributions of dust and ice, observation campaigns must be optimized. This requires a synchronized deployment of filters, carefully chosen to isolate the spectral bands of water, ice, and carbon dioxide ice from the continuum of dust, coupled with simultaneous polarimetric measurements. Only by listening to both the high and low registers of the cosmic duet simultaneously can we hope to understand the true composition and behavior of these visitors from other stars. The light curve is the final mix, but with the right instruments, we can isolate each individual track. Yet, as we perfect our ability to listen to this delicate balance between dust and ice, we must ask what happens when the composer itself, the comet's nucleus, decides to change the very rules of the performance as it approaches the furnace of the inner solar system. This leads us inexorably to the next profound transition. When a comet like the interstellar object Atlas journeys inward, past the frost line, it undergoes a fundamental metamorphosis in its very mode of material production. The gentle, sustained diffusion of surface dust gives way to something far more violent and transformative. What occurs when the quiet process of sublimation is replaced by the explosive detonation of subsurface ice? As the interstellar object designated 3I Atlas continued its inexorable journey sunward, crossing the threshold of 4 astronomical units, a fundamental transformation was observed in its very nature. The initial phase of its activity, characterized by a gentle, almost somnolent diffusion of surface dust, began to cease. In its place, a new and more dynamic mode of production emerged. The object ceased its passive shedding and instead began to exhibit what can only be described as microscopic outbursts, sudden and localized eruptions of material from deep within its subsurface matrix. The primary data, the light curve designated 8, exhibited a distinct and statistically significant break in its slope at this precise orbital distance, a clear fingerprint of a shift in the governing physical processes. Was this merely the expected response of a generic icy body to increasing solar flux, or were we witnessing the activation of a far more intricate and specialized system? The mainstream scientific explanation points to the well-understood physics of volatile sublimation. According to current models, as solar radiation intensifies, ice is trapped within the object, primarily water, carbon monoxide, and carbon dioxide begin to transition directly from a solid to a gaseous state. The pressure of these trapped gases builds beneath a surface crust until it finds a weakness, a fissure, or a pore through which it can violently escape, carrying with it a cloud of fine, refractory dust particles. This mechanism of jet formation is commonly invoked for comets within our own solar system, and it provides a plausible, energy-efficient framework for the observed increase in dust production and the subsequent change in the object's brightness. The laws of thermodynamics, it seems, offer a complete and sufficient narrative. Yet, the data from the deep field imaging campaigns presents an anomaly that this conventional model struggles to fully accommodate. The observed jets were not the broad, fan-like structures typical of many short-period comets. Instead, they appeared as highly collimated, narrow beams, all emanating in concert, suggesting sources that were not randomly distributed across the surface, but rather organized and focused. Furthermore, spectroscopic analysis of the ejected dust revealed a distinct shift towards smaller particle sizes with a significantly higher albedo, indicating a different composition and formation mechanism from the initial surface material. If these were simply random fractures, venting gas, why would the resulting plumes exhibit such precise collimation and compositional consistency? Could the internal structure of 3I Atlas be so uniquely engineered as to channel these energies with such remarkable efficiency? This leads us to a more speculative hypothesis. Imagine not a homogeneous lump of ice, but a complex porous matrix of frozen volatiles, crisscrossed by a network of capillary-like tubes, a microscopic plumbing system of sorts. These are not random cracks, but a pre-existing intricate network of conduits. As thermal stresses from the sun's heat propagate through the object, they do not create fractures arbitrarily. Instead, they act like keys, opening specific valves within this network at their thermal stress thresholds. Each micro-outburst is not an explosion, but a controlled, high-pressure release from a designated nozzle, propelling material outward in a tightly focused beam, a silent, invisible firework display on a microscopic scale. The shift from dispersed dust to collimated jets would then be a deliberate change in operational mode, a transition from a passive state to an active, pressurized one. What natural process could forge such a precise and responsive internal architecture? To fully grasp the implications, we must analyze this phenomenon across 3 escalating tiers of intensity. The first, and most conservative, interpretation is a simple increase in dust production. The rising solar energy flux uniformly raises the sublimation rate of subsurface ices, leading to a steady, global enhancement in the number of dust particles being released. This is a linear response, a predictable outcome of basic physical laws. The object is merely doing what any comet would do under similar circumstances, its behavior scaling directly with the incident energy. But does a linear response adequately explain the sudden, sharp break in the ATT light curve and the instantaneous switch to collimated jets. This brings us to the second, more forceful tier, a cascading sequence of micro-outbursts driven by trapped vapor pressure. Here, the process is not uniform but localized and episodic. Pockets of highly volatile ices, sealed beneath less volatile layers, undergo rapid sublimation. The pressure builds until it exceeds the tensile strength of the overlying material, resulting in a small, violent rupture. This creates a chain reaction, where the release of one pocket alters the thermal and mechanical environment, triggering the next. The object's activity becomes a staccato rhythm of tiny eruptions, a popcorn effect of pressurized vents. This model accounts for the episodic nature and the localized source points, aligning with the observed fireworks descriptor. Yet, one must wonder, what is the ultimate source of the structural integrity that contains these pressures until the precise moment of release? The third, and most extreme, interpretation posits a catastrophic, yet cyclical, structural failure. In this scenario, the increasing heat does not merely open small vents, it causes the wholesale collapse of the roof of a large, subsurface cavern composed primarily of ice. This sudden collapse exposes a vast reservoir of volatile ices to the vacuum of space, resulting in an immense, directional outburst of dust and gas. The geometry of the collapse, shaped by the object's rotation, could naturally create a fan-shaped plume that sweeps across our line of sight, with a period matching the object's own spin. The spectral shift towards smaller, brighter particles would be the natural result of the violent disintegration of the cavern's icy walls and the ejection of pristine, interior material that had never been space-weathered. This is a dramatic, high-energy process, one that walks the line between geology and astrophysics. But could such a violent process be so finely tuned as to produce the observed, repeating patterns without completely disrupting the object's structural coherence? The positive consequence of this entire sequence, regardless of which interpretive tier one favors, is that it provides a unique observational window. We are presented with a natural cosmic laboratory to probe the mechanics of what could be termed cold geology within an interstellar core. By analyzing the light signatures, the fluctuations in brightness, the polarization of the scattered light, the specific spectral lines of the ejected gases, we can infer the material strengths, the internal pressures, the thermal conductivity, and the fracture mechanics of this visitor from another star. The micro-outbursts of 3I Atlas are not merely a spectacle, they are a data stream, encoding the secrets of its internal constitution and the physical laws that govern its behavior in an alien environment. But if we can decipher the language of these light signatures, what deeper forces, acting upon the very particles themselves, might we then be able to perceive? For the observed fluctuations in brightness are not solely a product of the quantity of dust produced. They are a delicate dance between the dust and the forces that act upon it once it has left the surface. The precise patterns of brightening and dimming, the intricate variations in the light curve, must also be governed by what happens to these reflective particles as they enter the near environment of the object, a region dominated by two invisible but potent influences: the relentless push of solar radiation pressure and the complex shifting flows of outgassing vapor. The jets may create the dust, but it is these subsequent forces that sculpt its cloud and dictate its reflective properties. Could it be that the true message from 3I Atlas is not in the eruption of the dust, but in its subsequent, carefully choreographed motion? The cosmos orchestrates its grandest symphonies not with sound, but with light and force. In the silent theatre of the solar system, the sun's radiation pressure acts as an invisible conductor, an unwavering stream of photons exerting a gentle but persistent push on the minutest of particles. Meanwhile, outgassing is the sizzling, volatile brass section, erupting from the comet's nucleus in unpredictable gusts, carrying with it dust and volatiles into the void. Together, These two fundamental forces choreograph the fluctuating brightness of Comet 3 I Atlas, a dance of light and shadow played out against the backdrop of interstellar space. The comet's light curve, with its flickering, staccato rhythms, is their direct transcript. We can model this dance with Newtonian precision, calculating the acceleration of micron-sized grains as they are swept from the nucleus by carbon monoxide and water vapor, then subsequently pushed by the momentum of sunlight. The equations are clear, the physics seemingly straightforward. Yet, does the sheer complexity of the observed flickering suggest we are still missing a crucial voice in this cosmic ensemble? The initial data, a long sequence of images captured between June and September 2025, provided the first tangible clues. As the comet rotated, these deep exposure photographs revealed a fascinating phenomenon. Delicate tendrils of dust, fine as spider silk, were not simply streaming away from the sun in a constant tail. Instead, they were seen reorienting themselves in sync with the comet's rotational phase angle. A particle's trajectory, when traced, demanded the inclusion of both radiation pressure and outgassing force to accurately match its orbital path. Furthermore, multiband photometry unveiled a telling dissonance. The fluctuations in the blue and red wavelengths were not in phase. The blue light, scattered by smaller particles highly susceptible to radiation pressure, flickered with a different tempo than the red light, dominated by larger grains more influenced by outgassing. This spectral desynchronization is a clear fingerprint of particle size segregation by these two competing forces. But what if this segregation is not merely a chaotic byproduct, but a structured, almost engineered, process? This leads us to a more speculative hypothesis. Perhaps we are not observing simple physics, but a form of sophisticated propulsion. Imagine these fine dust jets not as passive plumes, but as arrays of microscopic light sails. These hypothetical cold jets could be composed of materials with peculiar photonic properties, structures that allow them to reorient the reflected beam of particles with deliberate precision. In this scenario, the non-periodic flickering on an hourly timescale is not noise, but a form of information-rich modulation, a consequence of a non-linear interaction between the steady push of sunlight and the impulsive shove of outgassing. The comet's coma becomes a dynamic lens, focusing and defocusing light not by chance, but through a complex, perhaps even intentional, interplay of forces. Could the anomalous phase shifts between blue and red light be the signature of a microscopic technology, optimizing its own trajectory, using the very forces of nature as its fuel and its rudder? Our analysis must therefore proceed on three distinct levels of intensity. At the most conservative, or light, level, we see the expected. Radiation pressure efficiently sweeps away the smallest dust grains, creating a short-lived brightening in the shorter wavelengths as they present a larger collective surface area to the sunday. This is the standard model, a comfortable and well-understood baseline. But is the standard model sufficient to explain the violent, rotating fan-like structures observed in the coma? This brings us to the stronger interpretation. Here, the outgassing jets are not uniform. They act as rotating nozzles, creating a sweeping fan-shaped plume. As this fan sweeps across our line of sight, it causes a periodic amplitude modulation in the comet's brightness, a predictable pattern tied directly to the nucleus's spin. Our dynamical models can replicate this, but they require a level of outgassing asymmetry and jet stability that pushes the boundaries of cometary science. What internal structure of the nucleus could sustain such focused and stable jets over months, resisting the torques that would normally disrupt them? The most extreme and most provocative level of analysis confronts the non-periodic flickering head-on. This is not a simple harmonic, it is a stutter, a seemingly chaotic series of brightenings and dimmings that defies conventional periodogram analysis. We propose that this is the hallmark of a non-linear interaction, a feedback loop where the outgassing itself is modulated by the heating from radiation pressure. A burst of gas releases a cloud of dust. The dust absorbs and re-radiates sunlight, heating the nucleus and triggering more outgassing in a complex, unpredictable cascade. The comet, in this view, is a non-linear thermodynamic system, teetering on the edge of chaos. But what if this chaos is merely a veil, obscuring a higher form of order we have not yet learned to perceive? The very techniques we use to navigate this complexity may, ironically, hold the key to our own future. The opportunity here is profound, extending far beyond the study of a single interstellar visitor. By observing the natural optimization of these particle dynamics, we are being offered a masterclass in propulsion physics. The way 3I Atlas seemingly manipulates radiation pressure and outgassing for effect mirrors our own nascent ambitions with solar sail technology. We are designing simple, large sheets to catch the photon breeze, but nature, or perhaps intelligence, appears to be using a fleet of microscopic sails, each one a tuned resonator, interacting with specific wavelengths. This suggests a path forward, the development of passive control systems for our own interstellar probes, where the sail material itself can be engineered to reorient or modulate its thrust without expending reaction mass, simply by interacting with light in a more sophisticated way. The comet's behavior is a live demonstration of advanced orbital mechanics at the smallest scales. Could the secrets to navigating the vast interstellar ocean be written in the flickering light of this enigmatic traveler? This intricate dance of forces, however, leaves another, even more subtle signature on the light itself, a signature that cannot be deciphered by brightness alone. It requires us to look at the very orientation of the light waves, to ask not just how bright, but in what direction the light is vibrating. For when we analyze the polarization of the light scattered from 3I Atlas, we encounter an anomaly so profound it challenges our fundamental understanding of cometary dust. At small phase angles, where we expect to see a gentle positive polarization, the data reveals a strong and negative polarization, a reversal of the expected order. This is not a mere variation, it is an inversion, a whisper of a structure far more complex than any simple grain of ice or rock. What strange geometry of dust, what architecture of alien material could possibly twist the light in such a contrary way? The light we receive is a message, a complex cipher written in intensity, spectrum, and polarization. For the typical comet, the rules of this cipher are well established. As the phase angle, the Sun-Comet observer angle narrows, the sunlight scattered by the cometary dust grains becomes increasingly polarized in a positive direction, its electric field vector oscillating perpendicular to the scattering plane. This is the predictable behavior of a cloud of irregular, absorbing particles. Yet, with the interstellar visitor 3I Atlas, the cipher is broken. At these small phase angles, its light does something extraordinary. It changes its sign. The polarization turns negative, deepening into a profound negative value, as if the very fabric of its light has been inverted. This is not merely a deviation, it is an optical rebellion against established cometary physics. What manner of dust could write its signature in such a contrary script? The mainstream explanation begins with the microstructure of the dust itself. Scientists suggest this could be due to a preponderance of exceptionally fine, submicron particles. According to current models, such small grains, particularly if they are rich in transparent ices or highly porous, can exhibit weak negative polarization at small phase angles through a mechanism known as coherent backscattering. When light enters a porous, fluffy aggregate, it can undergo multiple scattering events. Upon exiting nearly directly back towards the light source, these scattered waves can interfere constructively, enhancing the intensity but, under specific geometric conditions, flipping the polarization state. The data from observations in June, July and August of 2025 seem to support this, showing a polarization curve that is flatter in the red wavelengths and steeper in the blue, a spectral signature often associated with fine, icy grains whose scattering properties are less wavelength dependent. Could the answer then be as simple as an unusual overabundance of the smallest, most pristine constituents of cosmic dust? But that simple explanation fails to account for the depth and clarity of the negative polarization signal. Coherent backscattering in a random diffuse cloud of fine particles typically produces only a shallow negative branch, a subtle dip in the polarization curve. The signal from 3I Atlas is pronounced and unambiguous. This leads us to a more potent hypothesis. What if the individual grains are not merely small and porous, but possess a radically complex architecture? Imagine a grain with a fractal, multi-layered surface, a labyrinth of reentrant angles and microscopic cavities. As light penetrates this complex topography at a narrow phase angle, the phase shifts introduced by scattering from these intricate structures could lead to widespread destructive interference for the customary polarization state, while coherently enhancing the opposite, negative state. The grain itself becomes a microscopic interferometer, engineered to flip the polarization vector under a specific geometric key. Is the negative polarization a direct imprint of a geometry never before seen in our solar system? The data pushes us further, inviting a third, more extreme interpretation. The polarization does not behave as a static property. It shows subtle, yet perceptible, temporal variations that are not perfectly correlated with the comet's rotation or the sun's illumination. This anomaly points away from a purely structural explanation and towards a dynamic one. We must consider the environment of the coma itself. What if the particles are not just complex, but act as minuscule, oriented mirrors? Intense electrostatic charges, built up by the relentless ultraviolet radiation from the sun, could create powerful electric fields within the coma. These fields could align these fractal grains, turning them into a vast, shimmering field of snow mirrors. Their orientation would not be random, but directed, creating a polarized reflection that dominates the scattering signal. The negative polarization would then not be a product of the grain structure alone, but an emergent property of a choreographed electric dance in the coma, a dance whose steps change with the fluctuating solar wind. Could we be witnessing not the scattering from dust, but a form of polarized reflection from a dynamically organized plasma crystal? This profound anomaly, however, transforms from a puzzle into a powerful tool. If the negative polarization is indeed a unique fingerprint of 3I Atlas's exotic dust, it provides us with a real-time method to separate the dust from the gas, to dissect the coma not by chemistry alone, but by its fundamental light-scattering behavior. Polarization becomes a diagnostic blade. We can now envision a new discipline, polarization tomography. By mapping the polarization vectors across the coma over time, we can reconstruct the three-dimensional structure and dynamics of the dust outflow, tracing the jets and spirals of material as they are expelled from the nucleus. This technique would allow us to see the inner workings of an interstellar coma in a way never before possible, to watch as its hidden engine breathes and convulses. But what is the engine itself powered by? What volatile fuel, burning in the dark, drives such an unusual and active coma? This line of inquiry naturally draws our attention from the dust itself to the gases that propel it, to the primary driver of cometary activity. The initial spectroscopic analyses revealed another profound deviation, a chemical signature that marks this object as unequivocally alien. While most solar system comets are dominated by water ice, the outgassing from 3I Atlas is overwhelmingly dominated by carbon dioxide. The ratio of carbon dioxide to water is anomalously high, an order of magnitude greater than what is typical for even the most carbon dioxide-rich comets from our own Oort cloud. According to current models of planetary formation, this suggests an origin in a protoplanetary disk that was either exceedingly cold, preserving vast reservoirs of carbon dioxide, ice, or one with a unique chemical pathway that favored the formation and retention of carbon dioxide over water. Could its home system have been a place where water was scarce and carbon dioxide was the primary volatile? This immense reservoir of carbon dioxide has a direct and observable consequence: an early and vigorous onset of activity. Water ice requires a significant amount of solar energy to sublimate, becoming truly active only when a comet ventures relatively close to the sunday. Carbon dioxide, however, is a more volatile species. It sublimes at much lower temperatures, far out in the cold depths of a planetary system. This explains why 3I Atlas exhibited a rapid brightening at a heliocentric distance, where a water-dominated comet would still lie dormant and undetectable. Its light curve rose steeply, a beacon ignited not by water, but by the furious sublimation of carbon dioxide ice. The mainstream view would posit that we are simply seeing the expected behavior of a comet with a different, yet still natural, volatile composition. But does this fully account for the sheer scale and persistence of the carbon dioxide output? The speculative hypothesis must confront the longevity of this process. A comet's activity is a race between sublimation and the formation of a refractory crust, a lag deposit of dust that can insulate the underlying ices and quench the outgassing. For a carbon dioxide-dominated object to remain so intensely active as it approaches the Sun implies either a complete lack of this insulating layer or a mechanism that continuously refreshes the surface with pristine ice. One could propose that the nucleus is not a monolithic body, but a sprawling, porous matrix of carbon dioxide, ice and dust, more like a fractal snowbank than a solid dirt ball. As the surface sublimes, the entire structure is permeable enough to allow the gas to flow freely from the interior, preventing the buildup of a stable crust. The comet would not develop a traditional surface, but would instead erode from within, a self-sculpting cloud of icy aggregates. Is the nucleus of 3I Atlas not a single world, but a fragile, dissipating swarm? This leads to an even more extreme possibility, one that connects back to the anomalous polarization. What if the high carbon dioxide abundance is not primordial? The laws of physics dictate that intense ultraviolet radiation can drive complex photochemistry on icy surfaces, potentially breaking down more complex carbon-bearing molecules and reforming them into carbon dioxide. Could we be witnessing an object that is, in a very real sense, burning? A nucleus rich in organic compounds, subjected to millennia of interstellar radiation, might have developed a thick, reactive crust. As our Sun now heats it, this crust undergoes a form of photolytic combustion, producing carbon dioxide not from simple sublimation, but as the exhaust of a slow cosmic fire. This would account for both the high carbon dioxide ratio and the potentially unusual dust properties. The fractal, churned-up grains could be the soot and ash of this process. Are we observing not the primordial ices of a protoplanetary disk, but the weathered and chemically altered remains of a much more complex object? The interplay between this carbon dioxide-driven activity and the observed light is profound. The rapid outgassing creates an immense, tenuous coma, which scatters sunlight and creates the high-contrast image we see. But the carbon dioxide itself, and the water that is undoubtedly also present, can refreeze onto the dust grains in the cold outer coma, creating the very icy mantles that could be responsible for the unusual polarization signatures. The high carbon dioxide activity thus does not operate in isolation. It directly manufactures the conditions for the optical anomaly. The comet becomes a single integrated system where its volatile heart dictates the behavior of its dusty light. But if the carbon dioxide is so dominant, shaping both the comet's activity and its appearance, what other, more subtle chemical signatures might it be hiding? And what do they whisper about the distant cradle from which this traveller came? The early activation of Comet 3I Atlas Its anomalous brightening, while still deep in the outer solar system beyond the orbit of Jupiter, presents a thermodynamic puzzle. Conventional models dictate that a comet's journey into luminosity is a slow, deliberate awakening, primarily driven by the sublimation of water ice as solar radiation intensifies. At a distance of approximately 6 astronomical units, the Sun is but a faint star, and its warmth is insufficient to trigger the vigorous outgassing required for such a pronounced cometary coma. The initial data, however, tells a different story. The comet's light curve began its steady ascent from this vast distance, a faint but undeniable signature of activity in the profound cold. The trigger, it seems, was not water, but something else entirely. Could the key to this premature ignition lie not in the familiar, but in an exotic, volatile, waiting for just a moment to catalyze its own release? According to current models, the early activity of a comet is a subtle process, often attributed to the sublimation of more volatile ices like carbon monoxide. These molecules can transition directly from solid to gas at temperatures far lower than those required for water ice. The James Webb Space Telescope, with its unparalleled sensitivity in the infrared, detected the distinct spectroscopic signature of carbon dioxide gas enveloping the nucleus. This finding, in itself, is not extraordinary. Carbon dioxide is a common constituent of cometary ices. The anomaly lies in its abundance and its apparent role as the primary driver of activity. Scientists suggest this could be due to a surface layer rich in carbon dioxide frost, more readily exposed to the weak sunlight than the water ice buried beneath. The steady increase in brightness from 6 astronomical units would be consistent with the gradual warming and sublimation of this surface reservoir. Yet, if this were a simple, uniform process, would it not produce a more predictable, less pronounced curve of light? But that does not account for the efficiency of the process. The sheer volume of gas required to produce the observed coma and the subsequent dust lift, indicated by a measured increase in fine particulates and a shift toward a more neutral color, seems to exceed what is thermodynamically feasible. From simple carbon dioxide, ice, at that heliocentric distance, the energy budget does not balance. This discrepancy invites a more speculative hypothesis. Perhaps the carbon dioxide ice within 3I Atlas is not pure. It may be intricately mixed or doped with rare interstellar molecules collected during its long journey through the dark between stars. These exotic compounds, whose structures are unknown to our laboratories, could act as a catalytic substrate, effectively lowering the activation energy required for sublimation. In this scenario, the carbon dioxide does not merely sublimate, it is actively released by a chemical intermediary, a ghost in the machine of ice. What if the comet's early light was not a product of simple solar heating, but of a complex, pre-programmed chemistry waiting for its cue? This leads us to a 3-tiered analysis of the carbon dioxide's role, a hierarchy of escalating possibilities. The first, and most conservative interpretation posits that the carbon dioxide simply provided a stable activity baseline. As the most volatile component on the nucleus surface, it was the first to respond to the increasing solar flux, creating a gentle, persistent outgassing that lifted the fine, neutral-colored dust from the surface. This would account for the initial, smooth rise in the light curve, HT, a prelude to the main event. It is a gentle whisper of activity before the comet begins to shout, but is a whisper enough to explain the clarity of the signal from such a great distance? A stronger hypothesis suggests that the carbon dioxide did not act alone. Its sublimation may have been the trigger for a more energetic chain reaction. As the carbon dioxide gas escaped, it could have mechanically disrupted and exposed deeper, more complex ices, a mixture of carbon monoxide and formaldehyde, for instance. The sudden exposure and rapid sublimation of these ices would cause a short-term burst of activity, a spike superimposed on the steady light curve. This would explain the brief, intense brightening events observed in the data from May to July, events that a simple carbon dioxide model cannot reproduce. The carbon dioxide becomes a key, unlocking not just itself, but other, more volatile reserves. What other volatile cocktails might have been stirred by this initial release? The most extreme interpretation forces us to consider the internal structure of the nucleus. Imagine not a uniform layer of ice, but discrete, pressurized pockets of carbon dioxide gas, trapped beneath a fragile crust of less volatile material. As weak solar radiation permeated the surface, it subtly increased the pressure within these pockets, until the structural integrity of the overlying material was compromised. A catastrophic, simultaneous fracturing could then occur, not a gentle seepage but a violent, coordinated eruption. This would manifest as a sharp, discontinuous break in the slope of the light curve, HT, a sudden jump in brightness, as vast tracts of the nucleus surface are blown open, exposing fresh, volatile rich ice to the vacuum of space. The comet would not slowly awaken, it would tear open its own eyelids. Does the true structure of an interstellar object lie not in its homogeneous composition, but in its hidden, pressurized flaws? The implications of a carbon dioxide-rich composition extend far beyond these initial observations, reaching into the comet's future as it plunges toward its perihelion on the 29th of October, 2025. A typical comet, reliant on water ice, experiences its peak activity around perihelion and then rapidly fades as its surface becomes depleted of volatiles and coated with a refractory, insulating crust. But if 3I Atlas possesses a deep, massive reservoir of carbon dioxide, its post-perihelion behavior could be profoundly different. The lower sublimation temperature of carbon dioxide means that activity could be sustained for a much longer period, even as the comet recedes from the Sun into the cooling depths of the outer solar system. It would not simply shut down. Instead of becoming a dormant, fading target, it could remain an active, dynamic object for years, a persistent and invaluable target for post-perihelion observation. Will this interstellar visitor, having revealed its first secret, continue to offer its mysteries long after its closest approach to our Sun? This sustained activity, fueled by an anomalous volatile, would paint a complex and evolving portrait of the coma, a shroud of gas and dust whose reflective properties are in constant flux. The very light we see is a product of this dynamic interplay. Yet, the composition of the dust itself holds a deeper, more startling anomaly, one that challenges our understanding of cosmic chemistry and the very formation of planetary systems. For within the spectral analysis of the coma, a signal has emerged that should not, according to all conventional models, be so prominent, so forceful, so early in the object's approach. It is the signature of an element whose volatility and abundance tell a story not of simple ices, but of metallic vapors and a history of extreme heat. What could it mean when the cold heart of an interstellar comet beats with the spectral line of nickel, shining brighter and sooner than that of iron? The cosmos speaks in a language of light, a spectral code deciphered by our most powerful instruments. In the silent fall of 2025, as the world turned its telescopes toward the interstellar visitor designated 3I Atlas, it was the subtle, early whisper of nickel that first hinted at a profound anomaly. The established narrative of cosmic chemistry, written in the fiery forges of stellar cores, dictates a clear sequence. Iron, with its profoundly stable nucleus, should be the last great elemental pillar to stand against the rising thermal onslaught of a sun-approaching body. Its spectral signature should emerge late, a testament to its resilience. Yet, the data from those mid-year observations told a different story. Nickel, a more volatile metal, was singing its swan song prematurely, its emission lines brightening in the spectral data before those of iron, suggesting a chemical narrative unfolding under conditions we have yet to fully comprehend. What does it mean when the volatile messenger arrives before the stalwart one? According to current astrophysical models, the sequence of elemental sublimation The transition from solid ice or dust directly to gas is a strict function of temperature and binding energy. As a comet nears the Sun, its surface heats in a predictable gradient. Ices of water and carbon monoxide vaporize first, followed by more refractory materials. Metallic elements like iron and nickel, locked within silicate or carbonaceous dust grains, require significant thermal energy to be liberated. Scientists suggest that localized heating, perhaps from a fracture exposing a fresh, nickel-rich vein of material, could explain this premature signal. It is a plausible, if somewhat ad hoc, explanation for a single anomalous data point. But does a simple exposure of a different mineralogy fully account for the peculiar strength and the specific timing of this nickel signature, a strength that, at its peak, rivaled that of the more abundant iron? This is where the conventional explanation begins to fray at the edges, inviting a more speculative hypothesis. Imagine, for a moment, not a simple chunk of nickel-iron alloy, but a more exotic chemistry at play. On Earth, nickel can form a compound known as nickel carbonyl, a volatile liquid that decomposes at relatively low temperatures, depositing a thin, pure layer of metallic nickel onto surfaces, a process central to industrial metal refining. Could such a compound have formed in the protoplanetary disk of another star? If 3I Atlas carried reservoirs of nickel carbonyl ice within its matrix, the gentle warmth of the distant Sun would have been sufficient to trigger its sublimation and subsequent decomposition. The nickel would not simply be released as a gas, it would be gently baked out, plating the surrounding dust grains with a nanoscale metallic veneer. This would not be a bulk release of elemental vapor, but a surface-level metallization event. What if the object's chemistry was performing a feat of natural vapor deposition, a process we labor to replicate in our most advanced laboratories? The evidence, gleaned from medium-resolution spectra between June and August of 2025, provides a tantalizing, if indirect, corroboration. The data showed not only the premature nickel emission, but also a concurrent, subtle shift in the object's overall color towards a more neutral hue. The conventional interpretation would attribute such a color change to variations in the size distribution of dust particles or the cleansing of darker, organic mantles. It is a well-understood phenomenon in cometary science. However, the precise synchronicity with the nickel anomaly is difficult to dismiss. A thin coating of nickel, even in minute quantities, would dramatically alter the optical properties of a non-conductive dust grain, turning it into a more efficient mirror. The weak or delayed ion lines only deepen the mystery, suggesting that the nickel was being liberated by a mechanism that did not apply to its iron cousin. How else can we explain this coordinated dance of spectral emission and reflected light, if not through a transformative process affecting the very surfaces of the comet's constituent particles? To fully grasp the implications, we must engage in a tiered analysis, each level venturing further into the realm of the possible. At its most conservative, the trace amounts of gaseous nickel could have a minor effect on the comet's overall scattering properties, a slight perturbation in the complex light scattering models. This is a minimal intervention, requiring no new physics, only a refinement of our existing chemical inventories. But is the universe often so minimal in its demonstrations of novelty? At a more substantial level of interpretation, the hypothesis gains traction. The formation of a nanoscale nickel coating on a significant fraction of the dust population would create a temporary population of what could be termed mirror grains. These particles would possess a higher albedo, reflecting more sunlight and explaining the observed brightening and neutral color shift. The coma would for a time become a more effective reflector, its light curve shaped not just by the quantity of dust but by its quality. This would be a transient phenomenon, as the relentless solar wind and ultraviolet radiation would eventually sputter away this delicate metallic skin. But what if the process was not a single fleeting event? The most extreme and most profound interpretation proposes a cyclical process. Imagine a body with a heterogeneous interior, where pockets of nickel carbonyl ice are intermittently exposed to sunlight by the object's slow rotation and sporadic outgassing. Each exposure event would trigger a new wave of metallization, coating the dust and increasing the comet's albedo. As that coated dust is blown away by solar radiation pressure and the exposed reservoir is depleted, the process would cease and the albedo would drop until the next pocket is uncovered. This could induce hourly or daily oscillations in the object's brightness, a flickering not driven by rotation alone, but by an internal, chemical heartbeat. Are we witnessing not a static geological world, but a dynamic, self-plating chemical system on a grand scale? This leads us to a broader, more technologically suggestive perspective. The potential for natural vapor deposition in the vacuum of space, utilizing the gentle heat of a star, presents a staggering opportunity. It is a clue to a form of natural metallurgy, operating at temperatures far lower than any smelting furnace. The processes we are hypothesizing for 3I, Atlas, are not unlike those we are beginning to explore for manufacturing in space, using volatile metal compounds to create ultra-pure, thin film coatings on satellites or space station components. This object may be demonstrating a principle of materials science that could one day be harnessed to protect spacecraft from radiation or to create vast, lightweight mirrors for astronomy. Is this interstellar traveler not just a subject of study, but a potential tutor in advanced fabrication, demonstrating a technology refined over billions of years in another solar system? Yet, as we fix our gaze upon this shimmering metallic coma, we must confront a fundamental uncertainty. Our entire interpretation rests upon the light we receive, the precise fluctuations of the photometric curve. But how much of this recorded dance of light is an intrinsic property of the object, and how much is a phantom imposed by the complex geometry of our observation? The angle from which we view 3I Atlas, its trajectory against the dense backdrop of the Milky Way, and the subtle motions of our own planet, could all conspire to distort the very signals we so meticulously record. Could the anomalies we attribute to nickel plating and cyclical outgassing be, in part, a mere trick of the light, a cosmic mirage born from our particular vantage point? The light curve we analyze is not a pure signal emanating from a solitary celestial body traversing the void. It is, in its essence, a complex geometric projection, a convolution of the dynamic dance between the Earth, the Sun, and the distant object. The very ground upon which our observatories rest is not a fixed stage. It rotates, it wobbles, it breathes with tectonic sighs. These geodynamic influences, combined with our specific vantage point from a spinning planet in an elliptical orbit, impose their own subtle signature upon the photons we collect. The angle of observation shifts minutely but incessantly, altering the apparent path of the object against the stellar background, a phenomenon meticulously tracked by institutions like the Very Large Telescope in Chile and the Keck Observatory in Hawaii. The light curve, therefore, is not merely a record of the object's intrinsic variability, but a palimpsest upon which the geometry of our own solar system is indelibly inscribed. Could it be that the anomalies we seek are not out there, but are shadows cast by our own moving platform? This leads us to a more speculative hypothesis, one that challenges the very reality of the signal we are measuring. What if the observed dimmings, the so-called dips in luminosity, are not entirely real? Consider the possibility of phantom dips, illusory fluctuations born from the interplay of a densely packed stellar background and the artificial constellations we have placed in the sky. As our telescopes stare into the rich starfields near the galactic plane, the chance alignment of a faint, the variable background star, or the transient passage of a high-altitude satellite could superimpose a false signal of diminution upon a steady light source. The data from late September 2025 appears to lend some credence to this notion, showing increased scatter in photometric measurements, precisely when the field of view approached the dense stellar nursery of the Milky Way's core. The standard corrections for phase angle and air mass, while reducing the noise, failed to eliminate these distortions completely. Are we, in our quest for the extraordinary, merely documenting the mundane chaos of a crowded cosmos and an increasingly cluttered near-Earth environment? To unravel this enigma, we must engage in a tripartite analysis, ascending through escalating levels of interpretation. The first, and most conservative, level attributes the discrepancies to simple stellar contamination. A faint, unresolved binary system, or a pulsating red giant lying almost directly behind the target could, in principle, introduce low-amplitude noise that mimics a genuine astrophysical variation. This is the null hypothesis, the first line of defense for Occam's razor. Yet, does the persistence of these features across multiple filters and their peculiar timing truly align with the behavior of a random background variable? The second, more assertive level of analysis points to a potential aliasing effect tied to the terrestrial day. The data from July through September 2025, collected from geographically disparate observatories, revealed a curious pattern. The amplitude of the suspected anomalies varied with the longitude of the observer. This suggests a signal that is not locked to the sidereal clock of the cosmos, but to the rotational period of our own world. Could a systematic error, perhaps related to the diurnal cycle of atmospheric conditions or the thermal expansion of telescope components, be generating a persistent, a localized artifact that masquerades as an astrophysical event? The implication is that our instruments themselves, and the planet they are anchored to, are whispering secrets into the data stream. Secrets we have mistaken for a voice from the depths. This brings us to the third, and most extreme, level of interpretation, the possibility of artificial outbursts. The sudden, short-term brightening events reported by some observers could be the result of glints from rotating satellites or, more provocatively, from a coordinated train of low Earth orbit objects passing through the telescope's line of sight. A highly reflective surface on a satellite panel, catching the sun at just the right angle, could produce a transient flash that is recorded as a dramatic, yet entirely fictitious, outburst from the target. The timing of these events, often sporadic and poorly corroborated across different sites, fits the profile of an anthropogenic rather than a natural phenomenon. Have we, in the age of new space, begun to pollute our view of the universe not just with light, but with convincing false positives that challenge our very understanding of stellar stability? The path forward requires a practical solution, a methodological firewall against these terrestrial and near-Earth phantoms. The answer lies in a globally synchronized network of observatories, a web of eyes spanning multiple continents and hemispheres. Such a network could perform continuous, multi-point photometry, allowing for the immediate triangulation and identification of local artifacts. By cross-referencing data from sites in Chile, Hawaii, the Canary Islands, and Australia, a true astrophysical signal would remain consistent, while a satellite glint or an atmospheric ghost would appear only in a single data stream. Furthermore, observation schedules must be meticulously planned to avoid the densest stellar fields of the galactic plane, and data processing pipelines must integrate real-time satellite tracking databases to automatically flag and remove transits from known orbital objects. This rigorous, multi-pronged approach is the only way to cleanse the light curve, to strip away the layers of terrestrial interference and recover the pristine, physically standard signal we seek. But can we ever be certain that what remains is purely the voice of the cosmos, and not an echo of our own world's persistent hum? This relentless pursuit of a clean signal inevitably forces us to confront the most tantalizing and controversial reports of all the brief, brilliant flashes known as outbursts. If the dips are suspect, what then of these sudden, defiant increases in luminosity? The void between worlds is not truly empty, but filled with a tenuous, ever-shifting sea of dust and gas. It is against this backdrop that our visitor, 3I Atlas, has journeyed, a solitary traveller whose faint light we have strained to capture. In the meticulous photometric data gathered during those critical nights of July and August 2025, we find a series of subtle, almost ghostly, fluctuations. The light curve, that fundamental narrative of an object's activity, appears to twitch. For a few brief hours, the comet's brightness increased by approximately 0.3 to 0.5 magnitudes, a faint but statistically significant pulse. The initial, and most prudent, explanation points to the terrestrial atmosphere. The seeing, a measure of atmospheric turbulence, was variable on those nights. Could these brief enhancements simply be the result of a momentary clearing in our own turbulent air, a temporary stillness that allowed a sharper, and thus brighter, image of the comet's coma to reach our senses? Further analysis, meticulously subtracting the influence of background stars and modelling the point spread function, did indeed account for a portion of the signal. Yet, a residue of these events remained, their light curves possessing a distinct, smooth profile that atmospheric scintillation rarely mimics. And in the deepest processed images, a faint, corresponding broadening of the dust tail was tentatively identified, a whisper of an echo, suggesting that something more than improved seeing had occurred. If not an artifact of our own world, then what transient engine within the comet itself could ignite and then fall silent within the span of a single earthly night? The conventional toolkit of cometary science offers a plausible mechanism, a mini outburst. Comets are known for their spontaneity, for sudden releases of dust and gas that can alter their appearance in a matter of hours. The cause is often attributed to the violent transition of volatile ices, most notably water ice, from a solid to a gas. As sunlight penetrates the thin, dusty crust of a comet, it heats the ices beneath. Pressure builds in subterranean cavities until the overlying material fractures, creating a fresh, active vent that erupts with jets of gas and entrained dust. This model perfectly explains the observed short duration, brightening, and the concomitant slight expansion of the dust tail. The event would be localized, a small section of the nucleus's surface, momentarily shedding its mantle and revealing the volatile heart beneath. The energy required is modest, the physics well within the boundaries of our understanding of solar system bodies. It is a tidy, rational conclusion. But does this model fully account for the precise, almost rhythmic recurrence of some of these events, or the peculiar smoothness of their light curves, which lack the sharp onset and gradual decay typical of a simple pressure release explosion? This is where we must permit our speculation to venture beyond the established, to consider a more dynamic and perhaps more unsettling internal architecture. Imagine a hypothesis we might term the pulse. What if the core of 3I Atlas is not a monolithic homogeneous structure, but a fractured, porous matrix of ices and refractory materials, laced with pockets of more exotic supervolatile ices? As the comet rotates, its subsurface is subjected to extreme thermal gradients. The resulting stresses could cause the entire nucleus to undergo minute, rhythmic expansions and contractions, a form of thermal breathing. This gentle, global flexing would act as a bellows, systematically squeezing these isolated gas pockets. Instead of a violent, chaotic rupture, we would witness a controlled, almost predictable release of gas. A slow, sustained exhalation that would push a fine mist of dust into the coma, producing the very smooth, extended brightening and tail softening we have observed. It is a process more akin to geology than to simple sublimation, a slow, planetary heartbeat driving its transient atmosphere. Could the very structure of this interstellar object be such that it breathes its substance into the void? To fully grasp the implications, we must analyze these outbursts across a spectrum of potential intensity. At the most benign level, we have the micro-outburst, a release of energy so faint it brightens the comet by less than 0.3 magnitudes. These would be the comet's background whispers, the constant, small-scale activity of a complex surface shedding its skin grain by grain. They are the expected noise of an active world, and their study would provide a map of the most volatile, near-surface materials. But what if we escalate the scenario? Consider a stronger, more organized phenomenon, a chain of outbursts, not random, but locked in phase with the comet's own rotation. If multiple events were to be observed recurring at the same rotational phase, it would point unequivocally to a specific, persistent, active region on the nucleus. This would no longer be a story of random fractures, but of a fixed, geological feature, a weak spot, a permanent vent, or a fissure that becomes active only when facing the sun. The comet would then possess a permanent geography of activity, a face that it turns toward the solar wind. What secrets of its internal structure and thermal properties would such a clockwork pattern reveal? And then, we must confront the most extreme possibility. Could a sufficiently powerful outburst act as a trigger, causing a localized collapse of the nucleus itself? A cliff face, undercut by the force of the eruption, gives way. A section of the fragile crust, its structural integrity compromised, slides into the void. Such an event would be far more than a simple release of gas. It would be a transformative geological cataclysm on a miniature scale. The sudden exposure of a vast, fresh surface area of pristine ice would lead to a massive, sustained surge in outgassing. The geometry of the entire coma and tail could be irrevocably altered, the comet's jet dynamics rewritten in a single, violent episode. The light curve would tell a story not of a pulse, but of a rupture. This leads us to a profound and unsettling question. Are we watching a static, if active, body, or are we witnessing an object in the process of actively reshaping itself before our very eyes, its form as transient as its trajectory? The observational consequences are clear, yet daunting. To move from tantalizing hints to confirmed detection requires a new paradigm of observation. We cannot rely on sporadic measurements. We need a continuous, high-cadence watch, a photometric vigil that captures the comet's every flicker. This must be coupled with advanced morphological filtering to disentangle the true cometary signal from the ever-present noise of our atmosphere and the stellar background. If these outbursts are confirmed, they become more than mere curiosities. They become our only window into the fracture and outgassing mechanics occurring deep within the cold, alien core of this visitor. Each small pulse is a seismic event, a tremor that carries information about the internal structure and composition that we can never hope to directly probe. But to understand the full story written in its light, we must look beyond these transient flashes and examine the larger, more permanent shifts in its behavior. What greater transformation might be indicated by a fundamental, irreversible change in the very slope of its long-term brightness? For it was at a distance of approximately 3.3 astronomical units from the Sun that the light curve of 3I Atlas exhibited a more profound and lasting anomaly. The steady, predictable brightening that had characterized its approach was interrupted not by a spike, but by a kink, a distinct change in slope, a break in the narrative. This was not a momentary outburst, but a permanent transition, a before and an after. The conventional explanation points to a shift in the dominant volatile. As the comet moved inward, water ice, the most abundant ice in our own solar system, may have finally reached its sublimation temperature, taking over as the primary driver of activity from more exotic supervolatiles like carbon monoxide. This would naturally alter the energy balance and the dust production rate, manifesting as a change in the light curve's gradient. It is a logical, well-supported hypothesis, a story we have seen play out in countless other comets. Yet, the precise distance of 3.3 astronomical units gives one pause. Is it merely a coincidence, Or does this specific heliocentric distance mark a critical threshold for this particular object's internal physics? The mainstream model provides an answer, but it feels incomplete, a description of the phenomenon rather than an explanation of its unique character. This invites a more speculative interpretation. What if the break in the light curve signifies something far more fundamental than a simple change in the type of ice that is boiling away? What if it marks the moment when the internal structure of 3I Atlas could no longer withstand the increasing solar warmth? Imagine a surface not of uniform rock and ice, but a layered, complex crust. The break could signal the sudden collapse or sloughing off of a distinct, global layer of material, a fragile, insulating mantle that had until that point suppressed the true level of activity beneath. The comet would, in effect, be shedding its skin, revealing a new, more active surface layer to the sun's rays. The increase in brightness would then be not just due to higher temperatures, but to a radical increase in the surface area of exposed ice. This would be a singular, structural event, not a gradual process. Or, we might venture further. Could this transition point to a phase change within the nucleus itself? A bulk restructuring of the amorphous ice in its core, crystallizing and releasing trapped gases and energy in a significant, sustained pulse that permanently alters the comet's outgassing profile. The kink in the graph would then be a signature of a deep internal rearrangement, a thermodynamic milestone in the life of this interstellar wanderer. Are we observing not just a comet heating up, but a comet metamorphosing from one state of being into another? The implications of this are profound. If the outbursts are the short, sharp sentences in the story of 3I Atlas, then the break in the light curve is a new chapter. It suggests that the object is not a passive, simple ball of ice and dust, but a differentiated, complex body with a history written into its very structure. Each layer, each change in activity, is a page in that history. The shift at 3.3 astronomical units may be the key to reading its past. Did it form in a dense, cold protoplanetary disk far from its parent star, acquiring a thick mantle of fragile volatiles? Or does its structure bear the scars of a violent past, perhaps a close encounter with another body or its star that left it with a fractured and layered interior? The light curve break is a clue that the true nature of 3I Atlas is not merely chemical, but geological and historical. It forces us to ask whether we are studying a simple remnant of planetary formation or the weathered, transformed fragment of a much larger and perhaps very different world. What other secrets might be unlocked by deciphering the precise timing and meaning of this fundamental transition? And what would it tell us about the environment that forged this traveler from the depths of interstellar space?